Welcome everybody, my name is Chong. I'm Director of Product Engineering at Kionix. And Kionix is a MEMS manufacturer of inertial sensors. Today I'm going to give a talk titled Navigating a Complex Sensor World. And I don't necessarily mean the navigation application, but with the explosion of sensors really driven by the smartphone revolution. There's a lot of information out there, a lot of choices, some misinformation, and really it's a lot to take in. And so my hope is that this talk provides a little bit of a mental map, helping people figure their way through. And I was telling this gentleman in the front row that those among you who are experts at this, you may not learn that much because this is more of a general interest talk targeted to those who are looking at designing and putting sensors into their products. But hopefully everybody will walk away with something. So just a quick overview of where I'm coming from. At Kionix, we've been in the inertial sensor business since 1993. It was a spin-out of some technology at Cornell University, and it's grown over the years to become a top provider of MEMS accelerometers. This year is going to see our entry into other areas such as gyroscopes and magnetometers, and the software solutions such as sensor fusion. Most of our products are being built into consumer electronics, although we do have some in automotive and medical. And you'll find our products in devices such as smartphones and tablets, laptops, hard drives, game systems, and so on. Kionix designs the whole thing, the MEMS, the ASIC, packages them up, test them. We have our own foundry. And a couple of years ago, we were acquired by Rome, which is a big sponsor of this expo. So freedom. This is the promise of technology to free us from everyday mundane tasks, to empower us to do more. But what actually happens oftentimes is we have somewhat of a burden to interact with that technology. And as everybody knows, sometimes technology doesn't work right, and you have to configure it and go through menus and stuff. So what we're seeing these days is the promise of technology becoming a little bit more sophisticated and fading into the background. People love technology, but they really don't want to have to work to make it work for them. And so they want it to work in a natural way. So how does that happen? Well, the devices need to be a little bit more intelligent. They need, what the buzzword is, awareness. And that could be contextual awareness or situational awareness. But really it boils down to the device being aware of what's happening around it. And three core components of this are location, where it is, orientation, how it's pointed or how the user's, where it's looking, and motion, what's happening, how it's moving. And once you have that, you have the promise of a whole slew of applications. And I don't have smartphones up there because that's the obvious one. That's a mainstream one. That's the one that's pulling everybody else along with it. It certainly will continue to drive the decisions and the choices in the whole space. But what I'm seeing now also is that what smartphones have done for us, the smartphone revolution, is it's raised both awareness of what might be done and expectations. I mean, we want all of our other technical devices to also work for us in that way, be that intelligent. And some of the applications are indoor navigation, augmented reality, with the aging population and concerns for health that'll come in. There are things that monitor how you sleep and how you turn. We're a very data-driven society. We love data, so tracking fitness, the number of steps you take, the number of calories you burn, the number of strokes as you're swimming laps, how well your swing is in golf. All these things are applications that the inertial sensors promise to help out and make more sophisticated. And so to do that, the vendors or the manufacturers of these products need to embed sensor functionality into their products. And so my talk is divided into three sections. The first will be a high-level look at some of the major trends that are happening in the marketplace. And then I'll go on to how the pieces fit together. And again, that's where I'm hoping to provide a little bit of context and a little bit of an understanding of how all the things that are happening, the buzzwords, the products, the software, fits together. And then ultimately to give some insights into some considerations of what you might want as a device builder to think about if you're integrating a sensor, what types of sensors to choose, and what types of providers, or what aspects of a provider to look into. So to start out with the sensor trends, the way I've kind of organized it is, the middle column gives the obvious ones, the trends that we're right in, smack dab in the middle. And the column on the right is a little bit less clear. There are trends that may be coming, but how they'll take form is a little less certain. Now, size is the obvious trend because it enables us to put more and more into that amazing device that fits in our pocket or our purse. And so we're being driven to make the sensors smaller and smaller. 4x4s, 3x3s are the mainstream right now. Already out there are things that are below 2 millimeters square. But the question is whether it will continue to shrink past that, or will the size be small enough, will it plateau, and will added functionality or features be starting to be cropping into those? A similar trend is happening with price. The prices of sensors have dropped like a rock, and what that does is it makes them much more available and accessible to be built into devices. And again, in a similar fashion, where will that price start to plateau out? It's heading towards zero, but obviously it won't get there. And so where will it plateau, and where will, instead of dropping the price, we'll be adding to those sensors? Performance is an interesting one. Obviously we're getting new devices on the stage, but a couple of years, maybe a year or two ago, at least in the accelerometer world, which was the real starting point for all of this, the performance seemed to converge, and what you get from different manufacturers was roughly the same, and there wasn't a lot of differentiation. But what I'm hearing now is there may be another renewed interest in saying, how can we take the next step up in terms of performance? And it almost always boils down to stability and accuracy in order to enable new applications. Now, what's not clear in the performance trend is whether trade-offs will be allowed. It's easier to give you a higher performing sensor if you can allow more current, or you can allow a larger size. But what trade-offs will be acceptable, what won't, is up for grabs. And then the biggie is the combo sensors. The combination of sensors is the thrust that started last year and is really in full bloom this year. And the accelerometer and gyroscope combination is the one leading the way. There's also efforts to combine the accelerometer and the magnetometer, but it's not clear whether it'll have the same acceptance. And the 9-axis, where you put all three together, and then the 10-axis with pressure, giving you altitude information, are also talked about, but it's not anywhere near as close to being here. Now, the combination sensor trend is such a big trend that I wanted to spend a slide on it, and I think there are other talks either yesterday or today, tomorrow, that'll delve in it more deeply, but I did want to go over a little bit of the pros and the cons. Why would you combine sensors? Well, one of the main reasons is a reduction in cost versus the separate components. MEMS accelerometers, MEMS gyroscopes, they have a MEMS element, and then they have an ASIC. And so when you combine the two together, you still need a MEMS accelerometer, a MEMS gyroscope, for example, but you can use just a single ASIC. So you'll have a reduction of one component there. You'll also only have to go through one packaging step. You also need only to go through one testing step. And so there's a huge opportunity to reduce the cost. In a similar fashion, the smaller footprint is a promise. Because you can fit first of all, you throw out the need for a second ASIC. And in addition, you can put the two components together much more closely than you can as discrete parts on a circuit board. And lastly, you'll have better integration. These sensors really are siblings in that they're sensing the inertial activity around them, and so they'll benefit from better integration. As a system designer, you'll be able to talk with just a single sensor rather than having to worry about different protocols or different representations of the data. You'll be able to talk to just a single ASIC. They also have a promise of better power management. One of the Achilles heels of the gyro is that it's an active device. It's always moving in order to do its sensing. So you're always driving it. It's consuming 100 times more current than an accelerometer. So what is the typical application of combining them is turn off the gyro until it's needed. And if you're not moving, there's no need to keep looking and trying to output rotational speed. And so combining that and integrating that is a fundamental function of combining the sensors. And lastly, when you put the two sensors together, if you're going to make use of both sensors, a lot of times you want to know their alignment of the two axes. And you can achieve that to a higher degree of accuracy in a packaging house in a single package than you can as separate components on a board. So there are a lot of advantages. Why might you not? Well, the cost in some cases is not cheaper. I mean, the cost has been driven down by discretes so much, and the volumes are so high that at least at this time, you may actually be paying less if you go two separate sensors than a single combo sensor. You also have reduction in freedom of placement. Placing a single large sensor on a board, you're a little bit more restricted where you can place it versus two small sensors where you can fit it in open spaces. And lastly, you have less freedom to use the best of the breed. Not only are you now getting the same, using the same manufacturer for both sensors, but your choice is limited to what they decided to combine. So if there's a specific functionality or performance in a sensor that's not in a combination sensor, that's not available. So that's the hardware trends. Now if we look at the software trends, there's two very big ones. The first is standardization of software frameworks. And that's being driven by Android, Windows 8, and iOS. Android is out there, it has a lot of mind share. iOS is available, but if you're a hardware or device manufacturer, it's a closed system, you don't have availability. Windows 8 is got a lot of buzz coming, and it's going to be coming out in just a few months. What's not clear is what other platforms might arise or what other platforms might be out there. From another trend, and this is another biggie, is the sensor fusion. With these sensors, what can you do when you combine the data instead of dealing with them as separate streams of information? Now, this is in full bloom again, this year, and what the fusion is, was crystallizing a little bit. If you talk to a number of different manufacturers, how they might describe this a little bit different. But due to some of the standardization, I think there is a convergence as to what it is. Basically, it's a couple of standard outputs like a quaternion, which is really just telling you how you're pointed, linear acceleration, gravity. But what's not clear is how it's going to get done. It's an algorithm, and everybody's approaching it with their own insights and expertise. And so fusion algorithms are going to differ. And the other area that's not so clear is who's going to do it. It could be the sensor manufacturers, it could be the platform guys, it could be third-party people. And lastly, where is it going to be done? Is it going to be done, in the sensor itself, or is it going to be on a separate chip, or is it going to be done again in the application processor? So just to touch on those two trends, what are your choices as a system designer? Right now, again, iOS closed system, so I don't have that up here. Android already out there, already in substantial use. You'll find it being applied to anything from televisions to toaster ovens. What these platforms give you, the first two, is what standardization normally does. It lets you build upon the efforts of others so that you don't always have to reinvent the wheel. So Android is definitely one of the main choices out there. As I said, Windows 8 is a big choice, but it's limited to a smaller range of devices, mostly PCs, tablets, and the phone. It's not yet proven, but as I said, I think there are large expectations that it will be, a very viable and well-received platform. And lastly, you always have the choice to go the custom route. And with all those secondary applications that I mentioned earlier, this is often the route that they may go because they don't want the overhead of a standard platform, or they need it to fit into specific requirements. And that's what the custom platform gives you. It gives you a lot of freedom, and it offers the highest possible performance, but like going the custom route, in anything, you really have to shoulder a lot of the burden. Now, just a quick pros and cons of sensor fusion too, because that's such a major trend. Why might you combine data? Again, it provides a higher level of inertial information. Instead of having to deal with the acceleration in X, Y, and Z of this device, you're getting the orientation, or the tilt, or where gravity is, or where north is. Another reason is it presents the data in a very standard format. They're taking care of the combination of the data. So you don't have to worry that this device is sending the output at 50 hertz, and another device is at 200 hertz. And this device is 8-bit, and this device is 12-bit, and this device is 2's complement, and so on. The sensor fusion will take care of a lot of that complexity and let the system designer really focus on what they want to, what functionality they want to do. Why might you not? Now, there's not many reasons you wouldn't go this route, and that's why this is such a strong trend. The few that I could think of is, if you're already doing it and you're already in this market, you do have some new stuff to learn. It is an algorithm. It does require some computational power, and so you need to have that available to you. You may lose some, if you're only using the sensor fusion solution, you may lose some use of embedded algorithms. And embedded algorithms are those which are optimized by the sensor manufacturer for a specific purpose, such as screen rotation, or tap, or wake up. And lastly, and this is the most significant one, is sensor locking. With sensor fusion solutions, since they're dealing with a sensor at a low level, they need to specifically be designed to support that sensor brand, that sensor model. And so if you're using a solution, you may not have a lot of choice as to what sensors will work with that solution. So, that's the first part, which is kind of going over some high-level trends. Now what I'm hoping to do is give you some structure, some context to how these trends push the devices and the software to fit together. And so I'm starting out with just a very simple data flow map. Everything starts out with some motion or inactivity, which the raw sensor itself detects. And again, like I said, the sensors are going to be saying, I'm rotating this fast, or I'm sensing acceleration on X, Y, or Z. And then you have this area in the middle, which is trying to make the data a little bit more useful. You have low-level sensor data processing, or maybe you're buffering the data, accumulating it, so you can do more than detect what's happening at that moment, but you can detect what happened over a time sequence. Or you may have some embedded algorithms to fire and interrupt. Oh, something moved, let's wake everybody else up. Then you have the higher level data processing, which is taking that data and repackaging it in a more useful form. I'm sorry, it's kind of hard to see this yellow. But some of those things, as I said, was orientation, tilt, speed. And that's really what fundamentally a person or an application developer wants. So then that higher level information is fed up to the application, which then gives the user a certain experience. So how does this find its manifestation in the device itself? What I have here is some scenarios and kind of a progression over time in terms of how the pieces fall together. In the beginning, there was just an application processor and a sensor. And again, the sensor just output the raw data, and the application processor had to make use of it. Then sensors became a little bit more intelligent. People saw that there were specific uses for these, and they said, well, I'm going to take the load off of every individual customer, every individual developer, and I'm going to tell you when the screen rotates, or I'm going to tell you when I'm falling, free fall, or I'm going to tell you when a tap has occurred, in which direction. Now, with this API standardization, what you're getting is now the application layer in the application processor is becoming a little bit more sophisticated. It's saying, you know, I can't constantly be dealing with every individual sensor's quirks. I'm going to say I'm going to present a framework and a common foundation, and we need these sensors in the system. And so this is providing a little bit of standardization. And where we're going to is embedding the fusion capability someplace. And that might be in, as I said, a separate chip, or it might be in the sensor itself. So all of these are still active and in use. Again, this is really your choice if you're doing a custom solution. This is your choice if you're going to one of the standard platforms. And this is your choice, you know, this year and next, coming out onto the stage. And what are the benefits of this? Well, lots of easier integration for all the sensor combination, sensor fusion reasons I gave. Power reduction. A lot of times these hubs are going to have some programmability to them. And so they will let you do things in this low power portion of the system that would consume a lot of power up here, or a different thread, and so on. And honestly, one big driver for this too is not only the functionality, but the ability to differentiate. You're going to see different solutions, and they're not going to be as similar as the raw sensor data themselves. So you're going to have a lot more choices. I'm blowing through this. So my last section is really in what are your choices, and what might you want to consider if you're getting into this field when you're trying to choose a sensor or a sensor provider. I list 5 here. The first being cost. And cost comes into 2 forms. Comes into the obvious price, but then the power is nearly sometimes more important. Obviously, you're going to look for some performance and some features. Sensor fusion, as I said, there's not a lot of drawbacks. It's going to be there, and it's going to provide a lot of benefits. Support an ecosystem and manufacturing. So I was going to do a whole navigation theme to this, but I limited it to the iceberg analogy, partly in honor of the centennial of the Titanic. But you have the obvious cost of the sensor. But as the sensor goes down towards 0, that doesn't matter as much. And it's the other cost that people first starting out don't realize can be quite substantial. And when I say assembly and test, I mean, you know, as a device manufacturer, what you might have is you might be not understanding the real trade-offs or the real performance of a sensor, and so you build around something that can't be 100% provided for in terms of performance, so you'll have some yield loss possibly. Or you'll want to get more performance out by calibrating it after it's been put on the board, and after the orientation is known, and after any shifts to the reflow, and so on and so on. And so a number of manufacturers do want that performance, and so they actually calibrate on their assembly line, which means you've got to take off a board and you've got to move it around, and that's expensive. Now the other form of cost in terms of power has a similar iceberg analogy. It's very easy to go to a spec sheet and see a number for power, but more and more that does not represent, it's not as a valuable a number, and that's because the sensors have more and more modes of operation, because there's always trade-offs. If you want lower noise, maybe you accept a higher current, or you drop down the ODR, the output data rate, because you don't need the information as fast. And so understanding that there's no one number to describe the power draw of a sensor is important. And then lastly, power draw of a system is really what people people are concerned about. It's a little bit more difficult to get to, but the sensor can have a substantial impact on them because it can wake other parts of the system up or put them to sleep. And as I said, it can offload sensor fusion someplace, or it can say when a sensor fusion algorithm needs to start up. I'm not going to go through all of this, but it's more of a slide that if you're going to take the presentation home with you, you'll be looking at a host of performance and features, and obviously it depends on your application, what's important to you. But the one common one that I'm always hearing about is offset accuracy. Again, what is the ultimate accuracy or the ultimate limitations of any particular sensor? A lot of times, how stable is it? Because sensors, because they're mechanical devices, because they're made of a number of different materials, they're great thermometers. They will change their output over temperature even if they're not being moved. And we as manufacturers do our best to reduce that change. But you do want to know how that might change over temperature. Also after reflow, that's a very high temperature step which may cause some shifts in it, or after shock, or even over time. When you're looking for performance, you look at resolution. But having 16 bits of resolution with 4 bits of noise doesn't really give you much more than having 12 bits of resolution. So you want to take that into account. And then, if your algorithms are really trying to achieve something sophisticated, you'll want to know what other errors might be in the system, such as cross-axis and power. With magnetometers, you've got magnetic field rejection. I mean, the fields around us, the M fields, are changing all the time, and if you're trying to detect a very slight field from the Earth, you have to worry about trying to get through all the noise and the other dynamics and getting to what you truly want. And then there's a host of features. Sensor fusion. This is going to give you a lot of probably choices and sometimes difficulty making that choice. Obviously, certain algorithms are going to perform better than others. But even more than that, everybody's concerned about time to market and getting their product out there. And one thing that you want to know is, well, what's going to be the most transparent algorithm? What do I have the most ability to control or work with a vendor? How can I minimize my integration risks? And that might be risks of being able to do something or not, or timing risks. Because again, this is going to require, as sensor fusion develops, and before it's standardized, it's going to develop a lot of interaction with your system and the sensor provider. Sensor swapping without re-architecting. This is another big one. Because they're developed, the solutions, the sensor fusions developed for specific sensors, you want to make sure it's a flexible solution that can allow you to maybe bring in a different sensor from a different provider, or upgrade the sensor as time goes on, because you certainly don't want to be reinventing the wheel every time you want to rev your product. Completeness. If you're using it in the standard platforms, you want to make sure that it conforms to the requirements of those platforms. It provides all of the outputs. The computational MIPS and memory requirements may be important. And power management, how elegantly does it handle sensors turning on and off? Does it see a sensor powering down? Does the data drop out? Or does it handle it well? Does it turn the sensors on and off to provide a highly efficient algorithm? And what kind of calibration is needed, and what's that quality of calibration? And lastly, and this is again, it's trade-off between physics accuracy and psycho-visual effects. How is it implemented? This laser pointer is jittering around because I had too much coffee this morning, and that's not what I really want. I want that laser pointer to be very stable. And so there's a difference between accurately representing the motion and actually representing the motion that is desired. And so there are some effects that if you really showed how something's moving, an image would be jittering around and would cause dizziness. So it's that sort of thing that sometimes they actually introduce or limit the accuracy in order to provide a better experience. From the supported ecosystem, system, you know, this I believe is extremely important, and unfortunately, this is hard without being involved in a solution or a vendor to know ahead of time. You really just have to live through it. But what you'll find is that these things are critical, but not on a spec sheet. And that's how much technical and application support is out there. How quickly can they help you when something goes wrong, whether it's